Right, we're going to talk about the model of the Earth and what is GDA 2020 and Dynamic Datums. There's a lot of S-curves in this one. It's going to look scary. There's lots of words going to be up there, but the main reason is so I don't forget them, because it's all can be quite complicated. So I just want to introduce you gently to some of the concepts in projections, GDA 94, GDA 2020 and Dynamic Datums, all in a space of 15 minutes. And if you're an architect, don't let the engineers fool you that they know all about it. Most don't. It's only the surveyors in the room. They're the main ones who do actually know what this is all about. So surveyors, you can come into your own for this sort of work. First, a world coordinate system. How do we define a unique coordinate reference system that is applicable everywhere or anywhere in the world? If you're working with large projects and things, this is exactly what you need. And the most common solution has been longitude and latitude and, say, distance from the centre of the Earth. But what on earth is longitude and latitude? How do you define that? When what is the centre of the Earth? So with longitude and latitude, the first thing you've got to think about is the Earth is not what they taught you at school. It's not a nice sphere. It's actually flattened at the pole, so it's an ellipsoid. So that's the first little problem. And we actually define longitude and latitude in terms of an ellipsoid. And we don't usually talk about distance from the centre of the Earth. Those numbers get a little bit large, but tend to talk about the distance from the ellipsoid itself. So it's ellipsoid heights. That's what we mean by ellipsoid heights. But before you can define anything else, you have to define your ellipsoid. There's been many of them around over time. They tended to usually set them up with the centre of the Earth and a radius, so it sort of fitted your topography quite well. So there's the Airy 1830 was used in Britain. Clark 1858 was one in Australia. There's another one that was used for the ANS coordinates in 66 for the what we call the Australian geodetic datum. They all had different centres of the Earth, all had different radii for the major and minor axes. Now, what came along then was what's called GNSS or GPS, but now that Mr. Trump's in there, he'll probably charge you all to use the words GPS because that's an American thing. So GNSS is all the different satellite systems, because the Americans have one called GPS, but it's a whole lot of other ones. GLONASS, Galileo, Beidou, the Chinese one, an Indian one, and so on. So there's a lot more satellite systems out there you can use. But now, what's all about that with satellites is they all go around the mass centre of the Earth. You remember that from school. Was it someone's theorem that says it doesn't matter what the shape of the thing is, outside it works as a point source. So basically they all go around the one centre. And so it makes sense to have an ellipsoid where you put your centre at that mass centre of the Earth. None of the ellipsoids before ever did that. So the satellites have had a lot to do with it and the GPS. And this is what they now use, which is called GRS 80. That's got the values they use for the where the centre of the two axes and so on. That came around about in 1984. It originally was out. The Americans got it out by a few metres for the centre of the Earth, and it's been refined since then. So that's the one we tend to use now as our model of the Earth. So that's what we use for the geodetic datum of Australia, or MGA coordinates, and I'll come back and say what they actually are in a second. Now we have an ellipsoid, and its centre is the mass of the Earth, but how on earth, that's not very much. Here we've got our ellipsoid, but where on earth does it sit in space and things? So basically we want a North Pole. So they go to the North Star, and that's is a pretty fixed point, and so that's the North Pole. So you've got your ellipse, you've got now North Pole, it's been spinning around on that, you've got your South Pole, and the equator's halfway in between. So we've tied it down a little bit more. And the flattening of the ellipse occurs at the North and South Poles, and bulges at the equator. Right, now, longitude and latitude, we can finally talk about it. Basically, longitude is measured as a distance going around an angle, but from where? So basically they take it through Greenwich. That's your zero longitude, then you're taking degrees around from Greenwich. If you ever go to Greenwich, you'll see they've got a laser there, a green laser that's showing here's where zero longitude is. With latitude, we usually measure that from the equator, so you've got another angular measurement, north and south to give you those. So you've now tied down your longitude and latitude, so it can give you somewhere, anywhere on the Earth has unique longitude and latitude value, and also ellipsoid distance if you're talking about height. So basically, that's all very good, but how many people, you've got everything on for the whole Earth, but how many people want to work in longitude and latitude? You don't design longitude and latitude because the distances vary between 2 points depending on your longitude and latitude. So we use a map projection. And all a map projection is, you've got this darn sphere, which you can't pull out easily onto a flat bit of paper, so you project somehow onto some sort of thing. The simplest one is the plane. So you're going to put your plane on there. You'd come from the Earth centre, and it's actually slightly off there because it's ellipsoid, and you just project a point on the Earth up onto the paper, and that gives you your coordinates, your map projection coordinates. So every point can be then projected onto this sheet of paper. You can't get one sheet of paper for the whole of the Earth because it just can't be done. It's a mathematical impossibility. So we have to break it up usually. So basically you're projecting or rolling out onto a map projection. It's not usually an actual flat bit of paper. It's usually either a cylindrical or conical or some sort of cone, and you get all these different names for those sorts of things. The one we actually use is this secant transverse cylinder. The major thing is when you've got actually a map projection, there's a unique point from going from longitude, latitude to your map projection and then back. So if you've got a map projection coordinates, easting and northing, you can also get a unique longitude and latitude. So they're interchangeable. That's the very important thing about it. If you use some system of coordinates where 0, 0 is in the corner of the building, you have no idea what's going on. You can't easily get to longitude and latitude without knowing a lot about that site. So this can be done just with a GPS, and you can get the data backwards and forwards. So you're right, everything's set here, you can get unique points on the Earth. We call them easting and northings in a map projection, so it's different for different map projections, but we tend to call them easting and northings. And the one we use here is called the Universal Transverse Mercator, or UTM, if you're wondering about that buzzword. And what they do is they break the Earth up into 6-degree zones, and they're all well defined. The US military did this. I think it was all set up so they knew how to bomb you properly, so for the whole world. So that's the transverse Mercator. The cylinder's actually slightly, the Earth comes a bit wider, so that's why it's a secant transverse Mercator. And a scale factor, which we'll come to in a second, is 0.9996. So this is how the world's broken up into these UTMs. And I didn't lie, it was done by the military. They started this one. And most people in the world use a UTM system. Some countries are slightly different. Even in Australia, we use a few different ones because it depends if your country is going this way or the region talking or that way, you pick a different one to use. But Lambert conformal goes the other way and things like that. But the general world one is now UTMs. In Australia, we've got a number of these zones because we're very large, going from 50, 51, 52 over to 56. And down there in the middle of the zone, I put a dash thing there, that's called the central meridian of the zone. And it happens to be one here, I think, goes right through Brisbane. I think you're sitting just on the central meridian in Brisbane. Projection scale factor. What on earth's this? Well, on an ellipsoid, you get your distance between 2 points, but then you project this onto onto a plane or something else, and you get an X and Y coordinate. Heavens, the distance between those two things are not the same. And it's easy to see this by looking at a section through your Earth, and you're mapping onto this plane. If you've got 2 points on your Earth, P1 and P2, they'll map down to P1 dash and P2 dash on your plane. And you can see that obviously the distance on the ellipsoid is not the distance on the plane. So even though you're using map coordinates, they're not the same as ground coordinates. And we talk this thing about scale factor, that it's varying. As you walk across from one side to the other, it changes all the time, and you can get a number that when you multiply it will go from the distance on your grid to the ellipsoid, and that's called a scale factor. And here in Brisbane, it's about 0.996. So that's how it's distorted here, and as you move out left and right, it goes up to 1 and then drops off again. So that's for these MJ coordinates. The central meridian, which is Brisbane, is this 0.9996. Now you might think that makes very much difference, but it works out about 40 millimetres per 100 metres. So if you're asked to do things to a millimetre accuracy, if you don't worry about the scale factor, you'll go be screwed, because you're at about 400 millimetres per kilometre. Not much for some people, but when you're asked for millimetre accuracy, it's important. It's not that trivial, because we actually aren't on the ellipse, we're actually above it and below it. And the horrible thing about when you're talking about these coordinates is we're down here where we've got our projection plane, all the points on that dashed line go down to the 1 point. So they all, as far as the distance between all those points on your grid is identical. So friggin' hell, what do I do about that? Well, basically, we can work out the numbers depending on the height to make those sorts of adjustments. And that's called a combined scale factor. So if you really want to get from what you've got back to a real world ground distance, you've got to know your combined scale factor. And you might have noticed on some maps they actually say that somewhere. They say what is the combined scale factor. And that's so you can measure square root distance and get a ground distance from it. But it varies every point around the Earth. So we tend to only work in a small region with the one combined scale factor. So it all sounds messy, but if you follow the rules and know how to do it, it all works out. And that's what surveyors are trained to do, and they have to do it all the time. They take your work and make this all work for you. There's also a little other problem, is called, when we have vertical, it's not to the centre of the Earth. It depends on the mass underneath you exactly what we mean by vertical. We define vertical really by things have the same height if water doesn't flow between them. That's our measurement, and that's got nothing to do with the ellipsoids, the amount of iron and things like that underneath you. So there's another thing called a geoid, which defines that, and there's a thing called an end value, which gives you the distance between the geoid and that. So if you really want to get into that, you have to worry about that as well. And there's more corrections to go on there to fix all that up. But again, the surveyors do all that for you. Aren't they wonderful people? So in Australia, we use what's called the Australian height datum, which is these orthometric heights rather than ellipsoid heights. And you just have to know your end value everywhere to work it all out. Pretty trivial, eh? So now we have longitude and latitude, or say MJ mapping coordinates, and we've got a unique position anywhere in Australia or anywhere on the Earth, basically. And using combined scale factors, we can go from a square root distance on your map coordinates to ground distances on the ellipsoid. One small hitch. Continental drift. Basically, zero longitude is going through Greenwich, but Australia is moving away from Greenwich in the northeast direction of 7 centimetres per year towards the equator. So it's all right for the Brits, they're at zero all the time, but actually we're moving away. So our longitude and latitude actually changes every day. Now, it doesn't sound like very much. It's about the same rate that your fingernail grows. That's how much we're drifting. So our longitude and latitude is different every day. How in hell do we cope with this? And this will scare the living daylights out of you. We pick a fixed time to define longitude and latitude, and it's called an epoch. It's the only thing you remember. You can quote this at any time now. You say epoch. What is the epoch? It's a fancy word for time. So you pick an epoch and you say that's the time I'm going to say where Australia is. So basically, when they did GDA 94, they said we're going to say where everything in Australia is in 1994. So 1st of January. So right, that's great. So we have our map, our MJ coordinates, that's what they were all about. They used the universal transverse Mercator and the longitude and latitudes at 1st of January 1994. So what happens when Australia keeps moving? Well, it's all very simple. You get the real longitude and travel at the moment of the coordinates of where we are, and you move back to where it was on the 1st of January 1994. So when we talk about a coordinate, it's not where you actually are now in longitude and latitude or in easting, northing, it's where you were back in the 1st of January 1994. So even the longitude and latitudes are not actually straightforward. So you get a point, so if you change your model of the Earth, all those things can affect it. And just so you're aware, when we went from AGD 66 to GDA 94, we actually changed the model of the Earth. That's where we went to the one which is the mass-centred. And things moved by about 300 metres. So if you're using the longitude and latitude and you didn't say exactly what coordinate system, you could be out by 300 metres. Now with continental drift, we're actually moved by about 1.8 metres since we set it up in 1994. So it's very important to really know what you're talking about here. So what's happening is Australia, because we've moved 1.8 metres, they're coming up with a new thing called GDA 2020. So it's exactly the same ellipsoid we used before, but we're now going to fix where the longitude and latitudes are as of the 1st of January 2020. So all your coordinates are going to change again. So you're going to be out by about 1.8 metres if you don't know about that. So prepare for it, that's what this GDA 2020 is all about. Why am I telling you this? Well, you need to know basically everything has to be fine. If you are talking about being precise, everything, not just, you've got to know the mapping system, the dates, the epochs, the light, if you really want to tie down a project. And remember, keep saying epoch, epoch, epoch. Our continent's always moving, so we've got to allow for that, but it accumulates. No one worried about it too much in the past. Imagine with your GPS system, if you're driving down the centre of a line, it's out by 1.8 metres, you're out in the friggin' other lane. If your house has moved 1.8 metres, you'd be onto the next person's boundary and you could come and ask you to knock your house down. So you really do have to start worrying about these sort of things. Using values like, instead of using relative things, but absolute coordinates is called a coordinated geocadastre and that's the people's worry about it. It keeps moving, so you've got to know what you're talking about. So getting everything and all those definitions is extremely important. If you really want to be mischievous in life, just ask someone when they say, I'm going to put data into Google Earth, ask them what epoch it uses. I don't really know. I've never been able to find out. But you say, oh, in Australia we're using the 1994 epoch. In New Zealand they use 2000. So does Google Earth worry about that? What happens if you get 2020 data? So most people just say, oh, we're using GRS 80 or something like that. That's only the model of the Earth. You've got to then tie it down to the epoch. So going from GDA 94 to GDA 2020, which is with us now, and you say, huh? It's not 2020. What they worked out is how far we're going to move between now and 2020. So you get your coordinates today and you move them forward to 2020. So we're a little bit of ahead there. So we're already potentially using GDA 2020. In 12D, there are two methods defined for Australia. What's called a 7-parameter similarity transformation, i.e. a 3D helmet and anyone speak. But it works on longitude, latitude and ellipsoid height. And it goes to longitude, latitude, ellipsoid height. Then we project it back. But if you don't have ellipsoid heights, like you don't have for cadastre, that's useless to you. What they've also got is what is called an NTV2 grid, and this is just a thing that has said, look, for this longitude and latitude, this is where it's going to end up. And the government's producing that for all of Australia, and that's the one you tend to use. It's much more accurate than the 7-parameter similarity transform when they give it to high accuracy for us. So we've got a thing in there in 12D model, a bit like we had from the 94 one, where you can pick which one you're using and you can shift your data around. The government keeps saying, are we using 2020 yet? And we kept saying to them, well, where's your grid? Until we got a grid, we can't darn use it, but they have started producing and they're just coming out. So they've been advertising 2020 for ages, but it's just to get used to it. But now we do have the grids, it is possible. If you're in 12D model and you've got base and you're on maintenance, this will be included. The other one was in surveying module. This one will be there for everyone because you're all going to have to use it. Final thing, the dynamic datum. You're starting to hear a lot about this. You'll love this. Because now we're using large-scale electronic data, and everyone's got it, and it's being used everywhere, but you want it to a high precision. So the next move is what's called a dynamic datum. Because what happens with these satellites, they're going doo-doo-doo-doo, sitting up there, and what are they going to have for latitude? When they send you longitude and latitude, what's it going to send you? Well, they've got all these base stations around the world, and every year they say, oh, we're going to work out what we know where they are, we're going to work out what the new longitude and latitude of everything is. So every year the satellites are reset to what their longitude and latitude is, and when they send you the data, they send you that epoch. So the satellites are doing that every year without you realising it, but when you get your 94 coordinates, MGA 94, they get shifted back to 94. So basically your original data is coming out with longitude and latitude and a given epoch, that magic word. So why not store that original data rather than converting to some arbitrary time like 1994 or 2020? And that's called the dynamic datum. So it's all very simple. You're going to store your original data. Simple as that, that's all it is. Once you realise it keeps changing every year. So when we move to the dynamic datum, you're going to record the longitude and latitude and the epoch. You're going to keep that base data. The government will supply equations for moving the data backwards and forwards to different times. So imagine going from 94 to 2020, it'll be a shift of about 1.8 metres. So in a project, someone will decide what epoch they're going to use for a project. So you'll get all your data from all these different sources in different epochs and things and move them back to the specified project epoch. This is what's going to happen with the dynamic datum. So this is what will be going to happen in the future. So I ask you, what could go wrong? So thank you very much. That's all I have to say about that. Just remember, epoch. And ask people what their darn coordinates are, what the coordinate system is. You have to nail it down if you're talking about large-scale projects. Thank you.